Hello, everyone. We're going to go ahead and go over section 2.6, which is on transformations of functions. So we've learned a lot about functions at this point. Sections 2.4 and 2.5, those are on average rates of change and slope and working with real life problems. So we're kind of moving away from that again, going back to those kind of our early chapter 2 sections, mostly just focusing on functions themselves. And in this case, we're looking at transformations of functions. So as an overview, we can develop a better understanding of how to graph functions by learning how certain transformations of a function affect its graph. The idea of this section is that, yes, of course, we can always plot a new graph by creating a table of values, picking values of x, calculating those values of y. But the idea of this section is that we want to avoid putting in that extra work to plot points and to create points and create tables, tables of values and things like that. So we're looking at what indicators would transform our graph without us actually having to put in any effort into kind of recreating points or finding new points or creating tables of values. So really what this section is it is trying to be a shortcut. We're trying to understand how adding or subtracting, multiplying or dividing certain numbers in specific places in your function, how would that change your graph without putting in the extra effort of like recalculating values. So really that's kind of what we're getting at here in this section. But so the transformations that we're looking at are shifting, reflecting, and then stretching and shrinking. Stretching and shrinking are two separate transformations, but they occur very similar ways. So we kind of just lump those together. So we have three major transformations: shifting, reflecting, and then stretching and shrinking. So if we look at our little image here, this is actually going to be basically what we're doing. In this first one, we have shifting. We took the smiley face and we moved it over to the right in this case. So, it used to be here. We moved it over. Now it's on the right. So that was a shift. We shifted our smiley face. Then below here, we have a reflection. We see our smiley face is now upside down. So that's a reflection of our smiley face. And then we have our smiley face and it is stretched across horizontally there. That is our stretching and shrinking type of transformation that we see. So each one of these pictures represents the different three types of transformations that we're going to have. So, all right, let's go ahead and start with shifting. So like we said before, shifting would be having, something in one spot and moving it to the left or the right, or up and down. So we're going to have all four directions. We have vertical and horizontal shifting. So basically how shifting comes about is by adding or subtracting values from your function. So starting with vertical shifts of a graph, we suppose we have some number c and that c is positive. That's what we're stating here. So we're always going to assume that this number that we're adding or subtracting, it's positive. We don't have to think like, oh, what if it's negative and these cancel out? No, nothing like that. C is always positive. That's what that statement is getting at. But so our vertical shifts, starting with y is equal to f of x plus c. So we see here that we're adding this value to the outside of our function. And when we do that, that would shift our graph upward that many units. So if we had some function, let's say the function is x squared. If we had x squared plus 2, we would shift the graph of x squared up 2. So that's that idea there. And then it's opposite for subtraction. So to graph y is equal to f of x minus c, we would shift our graph down that many units, down c units. And we have two graphs here which are representing this. So this top one here is representing adding a value to your function. We see that that blue function was shifted up to the red function c. That's if you add a value to your function. And then we see over here, if we subtract that value, it's going to move down instead. So vertical shifts of a graph, these are fairly simple to grasp onto. You add a value, it moves up. You subtract a value, it moves down. Now, if we have horizontal shifts of a graph, we're actually going to have a little bit of an opposite type of reaction here. So horizontal shifts of a graph, once again, we're supposing that C is positive. And starting off, we say to graph y is equal to, and now we have f of x plus c. So instead of having f of x and then a plus c kind of tacked on to the end, we're now incorporating this plus c into our entire function. So we have f of x plus c, and this is going to shift the graph of y is equal to f of x to the left c units. So if you add a value within your function, you would shift to the left. Typically, we think if we add, we would probably shift to the right, but it is opposite in this case. The idea behind this is that your y values always have to stay the same. So your x values have to compensate for those values that you are adding or subtracting. So if your y value has to stay the same and you are adding, let's say 2 to x, x now has to be inherently 2 less to offset that plus 2. So that is kind of the reasoning behind this idea, that it's a little opposite than what we would imagine when it comes to horizontal shifts. So that's what we have here. So if we want to graph y is equal to f of x plus c, so adding that c to x directly, we would shift our graph f of x to the left that many units, so c units. And then opposite as well, if we want to graph y is equal to f of x minus c, meaning we've incorporated the minus c, we would shift our graph of y is equal to f of x to the right c units. So subtraction goes to the right, addition goes to the left when dealing with horizontal shifts there. So once again, we have some graphs here. This first one is representing that f of x minus c. So we see our blue graph going to the right to our red graph here. Then below we have f of x plus c. So we see that when we add that value of c, we move to the left here instead to this red graph. So those are going to be our vertical and horizontal shifts of our graph. Vertical is pretty, it aligns with what you would imagine. Horizontal shifts, opposite. So that is going to be a theme with almost all the transformations. You will see that, vertical transformations are what you would imagine. Horizontal transformations tend to be a little opposite. So we'll see that from now on. But let's go ahead and do an example. So example 1, we want to use the graph of f of x is equal to x squared, and we're going to help sketch the graph of each function. So for part A, we say g of x, our new function, is x squared plus 3. So we're adding a 3 to the outside. Then B, we have h of x is equal to x minus 4 squared. So that minus 4 is inside our function, so it's been incorporated. And C, we have j of x is equal to x plus 1 squared minus 2. So for part C, we do have both transformations going on. We have the horizontal one inside our parentheses and the vertical one on the outside of our function. So, all right, let's go ahead and head on over to our notes so we can go ahead and work on our problem. All right, so here we are with example 1. We have the graph of x squared redrawing here by me. So we have our graph here. Let's label our axes real quick. All right, this is actually more of the f of x axis there instead of y. There we go. All right, so we have part A, B, and C. A, we have g of x is equal to x squared plus 3. B, we have h of x is equal to x minus 4 squared. And C, we have j of x is equal to x plus 1 squared minus 2. So the first thing that we really want to do here is be able to identify what type of transformation is going on, kind of what it's doing, and things like that. So if we know our original function is x squared, for part A, the only thing that's changed is that we added this plus 3 at the end. So if we go back to our last slide or our notes, we can look at them and see that if we have our original function, and then it looks like we just added or subtracted a value on the end, that means we're going to have a vertical transformation. And since we're adding this value, we are going to vertically shift our graph up 3 units. So that is what this +3 here is telling us. We are going to vertically shift our graph up by 3 units. So we can go ahead and redraw our graph. Our graph is going to have the exact same shape. All we're doing is lifting it up 3. So when we lift it up 3, we know it's got this specific U shape to it. So let's go ahead, let's take that bottommost point, move that up 3, and then that's where we start with our U. So we're going to start here at 0, 0. We're going to move up 3. So that value there, this is going to be known as the vertex later on, but the vertex of our parabola, that lowest point, is moved up 3. So if I kind of recreate my parabola shape, we're now going to have this as represented as it being moved up 3. So if we recreate this shape here as best as we can, we're kind of going to get, a graph that looks a little bit like that. Doesn't need to be perfect. It just needs to have the main points to it here. So that is roughly what your graph would look like. The right-hand side is actually not that great. Let me redo that just a little bit here. All right, it's probably something a little more like that. So that is more of what we're looking for there for that graph of g of x. This was g of x here. And this original one was the graph of x squared, or just plainly the graph of f of x. All right, so that was part A. Let's go ahead and do part B. So we have h of x is equal to x minus 4, and all of that is squared. So looking at our notes from our lectures previously, we know that adding or subtracting a value directly to x within our function indicates a horizontal shift. And that's what's different about h of x versus f of x. We see instead of just x squared, it's now x minus 4 squared. So this minus 4 right here is the thing that is different about our function, and that's what's going to change or transform our function. So that minus 4, remember, horizontal, is a little opposite than what we would imagine. So that minus 4 is a horizontal shift, and it's going to be to the right. So we want to shift our graph horizontally to the right by 4 units. So that's what's going on here. All right, we're horizontally shifting our graph to the right by 4 units. So same as before, we're going to take that vertex point, that lowest point on our parabola, and we're going to shift that to the right by 4 units. And then we'll redraw our graph. So we're going to go 4 spaces to the right. Plot that vertex there, and now we just redraw our parabola. So, and it's okay if they cross over or anything like that. And this is h of x. So that is roughly what h of x would look like for our problem here. All right, so our last one here is part C. J of x is equal to x plus 1 squared plus minus 2. Sorry about that. So we have two different shifts going on here. We have the plus 1 that's inside of our function, inside the parentheses there, it's being squared. And we have a minus 2 out on the end. So we want to identify what each of these are going to do to our problem. The green color is just a tad bit light here. slightly better. So bear with me. All right, so we have x plus 1 squared and then minus 2. Let's actually just use a little bit of a darker color here. So we want to identify what this plus 1 and the minus 2 are both doing here. So if we look at just even the two problems that we did before, we saw that this number that's being added or subtracted kind of to the outside of that squared term, that's going to be a vertical shift. We added before and that moved it up. So if we're subtracting now, that means we're going to move down. So this minus 2 on the outside here, this is going to vertically shift our graph down by 2 units. All right, so we've got that going on. We have the vertical shift down. And with this plus 1 on the inside of our parentheses for x, that plus 1 is also being squared in this case, we see that this is going to be a horizontal shift. That value is being added on the inside of the parentheses. It's being incorporated, really only applying to x, not necessarily y. So this means we have a horizontal shift. And since we had subtraction last time and that made it go to the right, we have addition this time, which means it goes to the left. So this one here is a horizontal or horizontally shift our graph to the left. And this is by 1 unit. All right. The order in which we do these two things do not matter. You can pick whichever one, just came first or whichever one you like better. We'll end up in the same place either way. So let's go ahead. We're going to horizontally shift first and then vertically shift. So once again, taking that vertex of our parabola, we're going to go ahead and, wrong one. We are horizontally shifting to the left. So we shift 1 to the left, and then we're going to shift down 2. So our new vertex will be right about here. And now we can draw our parabola once again. So we can go ahead and draw. It's gonna roughly look something like this. We see a lot of these graphs, are kind of overlapping in this case, but this one was j of x. So we see that would be how we would graph using those horizontal and vertical shifts, how we would, move those graphs around and really what they would look like on a specific type of function. So, all right, that wraps up problem number 1. Let's go ahead and go back to our lecture and continue on. All right, just as a little visual before we go back to the lecture, we're going to take a look at Desmos here. Desmos has this really cool function so that if you add in a letter that is not X or Y, you can go ahead and you can make that into a slider. So in our case, we've turned A into a slider. We have two functions here. You can't quite see both of them because they're overlapping right now. But so we have Y is equal to X squared plus A and Y is equal to X squared minus A. So these are our vertical shifts. And if we play our slider, we see that this is what's happening when we are adding or subtracting a value to our function. So we see that x squared plus a is our red graph. The x squared minus a is our black graph here. And we see that they're moving up and down based on what the value of a is. So we see that a is going to be anywhere between 0 and 5, but for the red graph, we're adding it, so it's going up, and for the black graph, we are subtracting it, so it is going down instead. So this is a nice visual of kind of what's going on for these types of horizontal shifts, or sorry, vertical shifts, not horizontal. We're going to do horizontal right now. So We can do the same thing again. Once again, they're overlapping, so you only see one right now. But we have y is equal to, and now we have x plus b inside the parentheses squared, and we have x minus b inside those parentheses squared. So we have b as a slider once again. So if we press play, oh, let's get that a little differently. Here you can change the kind of settings of your slider. We still want it between 1 and 5, but we want this a little smoother than what we just saw. So our steps are going to go in 0.1 now instead. Whoop. Yes, that's what I want. All right, so they're a little smoother now, which is really nice. But so we see this value of b is changing just between the values of 0 and 5. So we kind of see the original plus the transformation. And we see that green graph, the one that is adding that value of b, is the one that is going to the left. The one that is subtracting that value of b is the one that's going to the right instead. Now it almost looks like they're switching, but they're not. The colors are staying the same. It's a very smooth transition there. But so we see that blue graph that goes to the right with subtraction. The addition is going to the left there instead. So once again, just a visual of kind of what those values do to your graph. So, all right, back to our lecture. We just finished up, that was example 1. Moving forward, we now have reflecting. So these are reflections. So before we saw the shifting, so kind of grabbing your graph, almost like a cut and paste type situation. You know, you're like cutting and then placing it anywhere else that you want. It looks the exact same. It's just somewhere else. Its location is different. With reflecting, you're taking your picture and you are flipping it up and down or side to side. So we're seeing that mirror effect. So like we have here with our smiley faces, we have our smiley face here is being reflected across this dotted line. So we're seeing that mirrored kind of up and down. So with reflecting a graph, really reflecting a graph comes about when you add a negative somewhere. That's really about it. So if we want to graph y is equal to negative f of x, so the negative is on the outside of your function, you would reflect your graph of y is equal to f of x in the x-axis. So this, whoop, there we go. I actually scrolled. So we have this first image here. If that negative is on the outside, you're going to be vertically reflecting. And this is known as going across the y-axis, sorry, across the x-axis, because this is the x-axis here. And we see that reflection is going across the x-axis. So we have that vertical reflection there. So like we said before, this kind of idea of something being kind of added on to the outside of your function, whether or not it's an addition or subtraction of a number or a negative, that usually indicates something vertical happening. If it's being applied just to the outside of your function, not directly to x, it's going to be a vertical transformation of some kind. So that's what we get when we add a negative to the outside of a function f of x. Then second, if we want to graph y is equal to f of negative x, we've now incorporated the negative. It's inside our function, only being applied to x. We would reflect our graph of y is equal to f of x across the y-axis. So that's that horizontal reflection, that left to right reflection there. And so we see it going across the y-axis here. And this is when we add in a negative directly to x. So we're really just affecting x in this case, not the entire function. So we see that's the type of reflection that occurs when we add the negative to the x versus the outside of the function. So, all right, let's go ahead, do an example. So example 2, we're going to sketch the graph of each function given the original. So the original and the graphs of the original we're going to have in our notes here. But so for part A, we have f of x is equal to negative x squared. And B, we have g of x is equal to the square root of negative x. So for A, f of x is equal to negative x squared. We imagine the original is x squared, just without the negative. And then for part B, g of x, we imagine the original was just the square root of x, not the square root of negative x. So we're going to go ahead and we're going to write and draw those original graphs in our notes, and then we'll sketch these new graphs as well. All right, so here we are with example 2. For example 2, part A, we had f of x was equal to negative x squared. So our original in this case would have been just plain x squared. So the original would have been something like f of x is equal to x squared, which is the graph that we see here plotted on our coordinate plane. So once again, we want to identify what's going on and how it's affecting our graph. So in this case, the only thing that's different is this negative on the outside of x squared. So if we have a negative being applied to the outside, so the entire function in this case, this indicates a vertical transformation. So in this case, we are having a vertical reflection, which means we will reflect across the x-axis. We're reflecting down, which means it's going around that x-axis. It's hinging at the x-axis. So we're reflecting across our x-axis. So if we want to redraw this graph, our vertex of our parabola, that lowest point, is going to stay the same. The only thing now is that it's going to face downwards instead of upwards. So if we go ahead and draw this in, we're going to go ahead and get our graph. Looks something a little bit like, that was not a great start, a little bit like this. So our graph of f of x in this case, negative x squared, it would look a little something like this. So it's the same graph, it's just been flipped over that x-axis. It had that vertical reflection. So let's go ahead and do part B. So we stated that g of x was equal to negative or square root of negative x. So the original in this case would have been the square root of x. So just without that negative there. But so we've identified the thing that's different is this negative. So now we want to go ahead and figure out what's happening, what kind of reflection is this? We see the negative is only being applied to the x value. It's not on the outside of our square root. It's only being applied to x, which means that it's horizontal. So this is going to be a horizontal reflection, which means that we're going to reflect across the y-axis now instead. So we see our function of the square root of x kind of, it goes up and veers off to the right. So our function g of x is going to veer off to the left instead. So we have the same kind of starting point, and then we can go ahead, mark a few points that will help us as more so just kind of guides. Something like that. And then we just want to make sure that our graph looks similar to the original. Good enough. Remember, does not have to be perfect, just has to be good enough. So you get the point. When you do your homework in WebAssign, you'll have tool plotters, so you won't really need to be hand drawing anything. The tool plotters will kind of do this for you, so you don't have to worry about making things absolutely perfect or not. But all right, so that's how we see kind of reflections occur within functions. So that wraps up problem 2. Let's go ahead and head on back over to our lecture. All right, so that was example 2. We're going to skip looking at this in Desmos just because there isn't a whole lot to look at, but we'll go back to Desmos to look at our next transformation here, which is stretching and shrinking. So of all the transformations, stretching and shrinking tend to be the more difficult ones to kind of grasp here. But like every other one, we have vertical and horizontal. And really the thing that changes between versus stretching or shrinking is just the actual value that you're multiplying by. Because you're multiplying, when it comes to stretching and shrinking, you're multiplying some number. But the idea is that it will change if that number is a fraction versus a whole number. So a number bigger than 1 or a number between 1 and 0. So that's really the difference we're going to see here for stretching and shrinking. But once again, we've got our smiley faces here. Here's our original smiley face. And then this is our smiley face that is stretched out, by its cheeks here. So it's horizontally stretched. And then over here we have a horizontal shrink. So we're kind of squishing it now, or compressing. Compressing is another word that we use to say shrinking instead. All right, so first we have vertical stretching and shrinking. Just like every other vertical transformation that we have, it's going to make a little bit more sense when it comes to what we're doing to our function. And then we'll get to horizontal. So vertical stretching and shrinking of graphs, we say that we have some graph y is equal to c times f of x. So we're multiplying this value of c to our function and the value of c, so it's going to change it from stretching or shrinking. So first off, if c is greater than 1, meaning that it's like, 2, 3, 4, 5, 100, whatever. If it's greater than 1, you would stretch that graph of y is equal to f of x, the original graph, vertically by a factor of c. So you're pulling it in this up and down kind of direction. And that's what we see in this very first graph here all the way to the left. Our original function's in blue, y is equal to f of x. And when we multiply by this value of c that's greater than 1, we see it kind of pulling. The lowest point gets lower and the highest point gets higher. So we see a lot of pulling going on there. So we're stretching it up and down. Then if c is between 0 and 1, meaning that it's most likely a fraction, it's like 1/2, a quarter, whatever, we're shrinking instead by that factor of c. So our second graph from the left here is representing that. So we have y is equal to f of x, our original. We said c was between 0 and 1. And when we multiply it, we're compressing. It's getting smaller in this case. So they're getting closer together. That high point gets lower, the low point kind of gets a little higher. So we're squishing it in this kind of up and down direction. So that's what happens when you have vertical stretching and shrinking. You're multiplying by a value of c to the outside of your function, and then c is either greater than 1 or between 0 and 1. So a fraction versus a whole number most likely. But we see that characteristic, that number is being multiplied by the entire function. It's on the outside. It's not being applied just to x, it's being applied to everything. So then we have horizontal stretching and shrinking of graphs. So before we get into this, I want to give you a little bit of like a mental visual before we explain what's going on here. If you imagine that you are holding a spring and you're not just like holding it relaxed, you're kind of squishing it a little bit, you're holding it. And we would call that the neutral position. You're holding it, but you're not putting like a whole lot of pressure. So it's not relaxed, but you're not like squeezing it really hard. So you've got this kind of neutral position here. If you lessen your strength, meaning that if you kind of let go, if you give half of your strength, that spring is going to spring outwards. It's going to get bigger, longer, more spread out when you kind of let go of that strength, that pressure that you're putting on your spring. And that's what happens here with horizontal stretching. Stretching occurs when that value of c that you're multiplying by is between 0 and 1, a fraction. So you're kind of letting go. You're letting it stretch out because you're not putting so much pressure on it. You have this small number being multiplied to your values of x that would allow it to kind of relax and stretch out. Now, opposite of that, if you're still holding it in that kind of neutral position, and instead you say, okay, I'm going to squeeze it, really hard. I'm going to put, maybe 2 or 3 times the pressure as I was doing before, and I'm going to shrink it. It's going to get smaller. And that's what happens with horizontal shrinking. You have some number c that is greater than 1 being multiplied by your values of x, and it would make it shrink by a factor of 1 over c in this case. So if c is 2, you're giving it double the strength for it to shrink about half the size. And before, if you stretched it, if you released your grip about half, you released about half that pressure, that spring is going to spring out about double its size. 1 over 1/2 is 2, so it would double in size if you kind of released half that pressure. So this is the idea behind horizontal stretching and shrinking of graphs. If you keep this idea with you, it may help a little bit. If it didn't, then it didn't. I'm sorry, but horizontal stretching and shrinking is probably the hardest one, toughest one to kind of grasp. But that is probably the best visual I've come up with over the years. So let's go ahead and read it out. So to graph this function, y is equal to f of c times x. So we see that value of c, it's inside your function. It's being applied just to x, not the entire function. So we say if c is greater than 1, so 2, 3, 5, 100, we would shrink our graph, our original graph, horizontally by a factor of 1 over c. So that was, twice the strength to get half the spring. So it would shrink about halfway if we put twice the amount of pressure. And this is what we see in this third graph here. We have our original f of x graph in blue, and our f of c times x, that graph here, is about half its size horizontally. It looks like it definitely got squished inwards there when c was greater than 1. Then we have if c is between the values of 0 and 1, meaning most likely a fraction of some kind, we would stretch that graph of our original function horizontally by a factor of, again, 1 over c. Since this number is between 0 and 1, when you divide, or when you kind of have this factor of 1 over c, it means that you would flip your numerator and denominator. So if c were 1/2, you're stretching by a factor of 2, because it's 1 over 1/2, which is 2. That's kind of that idea. It's a little more extra calculating that has to go into that. So here we see this very last graph. This is horizontally stretching. So we see we have the original blue graph, y is equal to f of x. And when c is between 0 and 1, we see it kind of relax out. It's going to stretch horizontally in both directions here. It gets about double the size long ways, and it relaxes. We don't see that kind of tight curves anymore. They're a lot longer, kind of looser. So, all right, that is the rundown on stretching and shrinking. So let's go ahead and do an example. So example 3, we have the graph of y is equal to f of x is shown below. We're going to sketch the graph of each function, a, b, and c. A is f of 2 times x. B is 2 times f of x. And c is 1/2 times f of 1/2 times x. So got quite a few things going on here. But this is our original graph of f of x. A lot of the time when it comes to shrinking and stretching, you will get kind of these pretend functions, because on real functions that you see more often, they're just not as exciting. They're not that interesting to look at. So whenever you have problems like these, they're most likely going to be imaginary functions, just a picture of it saying, this is the graph, transform it kind of thing. So this is our graph here. We kind of see we've got a lot of triangles here. Each triangle looks to have this kind of base length as 1 and a height of 1. It's going to help us a lot when it comes to graphing each one of our new functions. So, all right, let's go ahead and go over to our notes to work on this problem. All right, so here we are with example 3. We have our redrawn graph. I did, best I could. Here we are. So f of x. We have these triangles that are kind of set up. They've got that base of 1, the height of 1. And so we're going to see how our transformations change with each one of our new functions. So starting off with part A, then we want to redraw them as well. So starting with part A, we have f of 2 times x. So the thing that is changing here is this 2. We're multiplying x by 2. And when we multiply x by 2, we have this direct thing that is influencing x. So the fact that it is inside the parentheses right off the bat should tell you that this is a horizontal type of transformation. So what we have here is that this is going to horizontally, and now we have to decide if it's going to shrink or stretch. So if we know that this is horizontally, this value of c is greater than 1, it's 2. So we can imagine, we're putting twice that pressure on our spring. So our spring is shrinking. So that 2 that's greater than, 1, c greater than 1, we are horizontally going to shrink our graph. And we're talking about our original graph. We're horizontally shrink our graph by a factor of, and now is what we want to remember, that when it comes to horizontal shrinking and stretching, your factor is 1 over the value of c. So in this case, our value of c is 2, so we're shrinking by a factor of 1 over 2, which means shrinking by a factor of 1/2. It's going to be half the size because we put in twice the pressure. And then we want to redraw our graph. So since we have these triangles, that it kind of helps us, because now what this is telling us is that if we're shrinking, we're compressing these triangles, their height stays the same. Our height isn't changing, but those base values of your triangle are going to be half the size. So in our original function, the base of each triangle was 1, and if we're saying that it's going to have half the base, they now all will have a base of 1/2 instead. So we're going to see much skinnier triangles here. So let's go ahead and kind of fill in some helpful values here. So we kind of put in the half notches. So when we draw our graph, they will have the same height and half the width. So we can draw these, we can draw as many as we want. And then when we're done, we just kind of put little dots to represent. There's more, but I'm tired of this. So, so that's the idea there. So we can draw in, the other side as well. We want to get, as accurate as possible. Once again, they don't need to be perfect. They just need to look correct. So this is kind of what we're going for here. We saw much skinnier triangles. We're now fitting a lot more in this space. So we horizontally, we shrunk those on our graph. So, all right, let's go ahead and do part B. So for part B, we now have 2 times f of x. So the number that is affecting our function here is 2, and it's on the outside of our function. It's being applied to all values, not just x. And so when this is happening, we're essentially taking 2 times f of x, which is y. So we have 2 times y. So what's changing here is the height of our triangles, not the base. So since our number is outside f of x, we can verify that this is going to vertically. That value of 2 is greater than 1. When it comes to vertical, we are just going to stretch by that number. So c is greater than 1, we are stretching. So we are stretching by 2. So we're going to have a vertical stretch by a factor of 2. So when we draw our triangles now, they're going to have that same base, but they're going to be a lot taller. So when we draw our triangles, we're going to go ahead, they're going to have heights of 2. So we've got these really tall triangles. Their width is the exact same because we did not transform x, we only transformed y. But so we see they're very tall now. We can fill in the rest. So compared to our original graph, which you kind of see there right at the top, if we compare, they have the same width, they're just a lot taller. They have heights of 2 instead of having a height of 1. So, all right, that was part B. Lastly, we have part C. So now we have 2 transformations. We have 1/2 times f of 1/2 x. So we've got the 1/2 on the outside and the 1/2 on the inside affecting our function. So let's, wrong thing. Let's go ahead and start with the 1/2 that's on the outside of our function. We said just before, if it's on the outside, it's vertical. And in this case, our value of c is less than 1. It's between 0 and 1. So instead of a stretch, we now have a shrink. So we are going to vertically shrink. And whenever you vertically shrink or stretch, it's just by the factor of that number. So we're going to vertically shrink by a factor of 1/2. Then we want to deal with the other 1/2 we have here. So the 1/2 that is being multiplied by x, now not affecting the entire function, but just x. So it's inside the parentheses, tells us right away it's going to be horizontal. So we're going to horizontally. And this number is between 0 and 1. We imagine we're holding that spring. We're going to give it half the strength, half the pressure. That spring is going to bounce out to be double the size. So we see we're releasing, it's getting bigger. So we are horizontally stretching. So we horizontally stretch by a factor of, and it's 1 over that number. So we have 1/2, so our factor is 1 over 1/2, which means it's by a factor of 2. So this is what we need to be drawing here. So starting with the vertical shrink by a factor of 1/2, we're now going to have triangles with a height of 1/2 instead of 1. And then also we're going to horizontally stretch by a factor of 2, which means our triangles will have we'll have widths of 2 instead of 1. So we're going to see it be half the height, double the width. So we're going to have very short, wide triangles now. Let's go ahead and just label the kind of 1/2 mark here on our graph. Now let's go ahead and draw out our short and squat triangles. So that's kind of what we're looking at. We've got half the height, twice the width. And we imagine, that's going to go on. So we can draw a few more here. So these very kind of squat and short triangles. So that was what we saw for those transformations with that kind of combination that we had there. So when it comes to combinations, it's always best to identify what each one is doing separately and then use both of those when you regraph your function. So, all right, that wraps up example 3 here. So let's go ahead and head back on over to our lecture. All right, so that was example 3. That was the last transformation that we really had to deal with in this case. Let's go ahead and look at Desmos really quick as well to just get, a visual of this. All right, so here we are at Desmos. We're going to look at vertical transformations first. This is what's called the sine curve. Don't worry about the actual function itself. It's just a function that's going to give you the best kind of imagery here. But so we've got, this curve is wavy. And so we're going to see we have a, which is going to be the numbers between, 0 and 1. I put 0.1, but it's just supposed to be really small. It's actually do 0.01. But so it's just a small number, very close to 0. And then we have b, which is going to be between 1 and 5. So that's, larger than 1. So we're going to see the red graph when they kind of pop out. The red graph will be the shrink because that is the number between 0 and 1. And then b is going to be that stretch because it's greater than 1. So let's go ahead and watch these, try and get them around the same time. So we see the red graph is shrinking. It's kind of getting closer in size to that x-axis, and the black graph is the one that's being stretched in that case. So you see a lot of that stretching going on with that black graph and then shrinking with the red one. So, all right, so that's what it looks like when you have vertical transformations. Now let's go ahead and look at the horizontal ones here. So we have y is equal to sine of a times x. So we see that a and b is incorporated inside the function. And so a is going to be that stretch because it's between 0 and 1, and b is going to be that shrink because it is greater than 1. So let's go ahead and watch these. So we see the purple one with the larger values. They look like they're getting really kind of squished. And that red graph is definitely getting like very elongated, very stretched out. In that case, it's getting a lot longer, while the purple one is getting a lot tighter, a lot closer in, because we have these larger values for B and smaller values for A. So, all right, just a nice imagery. If you want to do this on your own, this would be kind of, how you'd set it up in Desmos if you want to try this out at home. But all right, let's go ahead and finish up our lecture. All right, so here is a summary of all the different transformations, just in a nice, graph by itself. Here we have this chart. So we have the different types of transformations, whether it's vertical or horizontal, and then the actual transformations themselves. So shifting, reflecting, shrinking, and stretching. Since this is a recorded lecture, I highly recommend that you pause at this point, copy this information down, and then we're going to move on here. So last idea that we have here is even and odd functions. So these are not transformations, but they are going to give us a little bit more information about functions themselves. Even and odd functions, we have f is some function. And the idea here is that if we add negative to x, meaning that if we tried to horizontally reflect a function here, if we tried to reflect across the y-axis, we would see that a function is even if we reflect across the y-axis and it looks the exact mirror image. So we would say that f of negative x was equal to f of x for all x in the domain of f. So we have this first graph here. This is an even graph. We see that when we had that original side of our graph f of x, when we flipped it across that y-axis, it looked like the exact mirror image, the exact reflection there. And this means that our function is even. It's even because it is symmetric to each half there. Then we have a function is odd if f of negative x is equal to f of x for all x in your domain of your function. So we see this graph here, the second one, we say the graph of an odd function is symmetric with respect to the origin. So we see this kind of diagonal symmetry in this case. Whenever you have a function that is odd, it's going to go through the origin like this, and then we have that origin symmetry. So if this sounds familiar at all, because if we remember, we learned about symmetry back in section 1.9. So we're seeing this again. We're seeing symmetry, but in this case, we have symmetry to the y-axis and we have symmetry to the origin. We no longer deal with symmetry to the x-axis because that is not a function, but we see that we can have symmetry to the y-axis and symmetry to the origin. So this is an idea that's come up again. We just have another new name for it, but it's the same idea. We could solve for the symmetry the exact same way as we did before. We're adding in a negative x and seeing what we get as a result. So let's go ahead and do an example. We're going to determine whether the function is even, odd, or neither. So we have a is f of x is equal to x to the power of 5 plus x. B is g of x is equal to 1 minus x to the power of 4. And C is h of x is equal to 2x minus x squared. So let's go ahead and work on this problem in our notes. All right, so problem 4, we have a function is even. If we replace x with negative x, we should get f of x as a result, so the original function. If it's odd, we replace x with negative x, and our function will come out as the negative version of our original function if it's odd. So really all we're going to do each time is just replace x with negative x and see what we get as a result. So for part A, we have f of x is equal to x to the power of 5 plus x. So let's go ahead and try out f of negative x. So remember, we're replacing every x with a negative x. So any powers that we have are being applied to everything. So the negatives included. And so if we simplify this, if you have a negative number raised to an odd power, that is basically going to be the negative version of the x, in this case, to the power of 5. So negative x to the power of 5. Since 5 is an odd power, that negative is going to stay, but it's going to be on the outside now. So it's going to be negative x to the power of 5. Then we have plus negative x, which is the same thing as saying minus x. And if we write this out, we can notice something. The original function was positive x to the power of 5 plus x. And when we plugged in negative x, we got negative x to the power of 5 minus x. So we saw the sign of each term change. So this is really negative f of x. And if this is negative f of x, that means our function has to be odd. So our function was odd because when we replace x with negative x, we got the negative version of our original function out. So that's how we determined that that was odd. Let's go ahead and do part B. Part B, we have g of x is equal to 1 minus x to the power of 4. We're going to replace x with negative x. So we'll have 1 minus negative x to the power of 4. So if you have a negative number and raise it to an even power, it's going to be positive. So negative x to the power of 4 is the same thing as positive x to the power of 4. So this is equal to 1 minus x to the power of 4, which is the original. This is equal to g of x. So since it was equal to the original, this means that our function was even. We said that our function's even if we replace x with negative x, and we get the same original function out as an answer. So now we can do our last one here. H of x is equal to 2x minus x squared. We're replacing x with negative x. So we'll have h of negative x. And we'll get 2 times negative x minus negative x squared. So 2 times negative x is going to give us a negative 2x. And then negative x squared is going to be x squared. It simplifies to just x squared. So we have negative 2x minus x squared. And if we look at our function, we did not change the sign of each term. 2x became negative 2x, but minus x squared stayed minus x squared. So we don't have the original and we don't have the negative version. So this is neither. It is not even or odd. And in most cases, most functions probably won't be either. They won't be odd and they won't be even. They'll be neither, like part C here. But it is nice if they're even or odd. It would help you, when you graph functions or use transformations or things like that. And also you will just be asked in general to find out if a function's even or odd from now on. So definitely expect that. One other way that is a little bit of a trick, and it helps a lot to figure out if a function's even or odd without plugging in negative x, is that functions that are even have even powers. And when we say even powers, we're going to include 0. So x to the power of 0, which is just 1, is going to be considered an even power. A function that is odd will have only odd powers. And this includes 1. So if we look at our function here for part A, we know it's odd already. But we have x to the power of 5, and 5 is an odd number. And then we have x, which is really x to the power of 1, and 1 is also an odd number. So in this case, our function is made up of x's that only have odd number powers. This will automatically tell us that this function is odd because it has odd numbered powers. So if we look then at part B as well, we have 1 minus x to the power of 4. 1 is just a constant number, but we can always tag a little x to the power of 0 on it. Because x to the power of 0 is just 1, so any constant technically is x to the power of 0. So if we have 1 minus x to the power of 4, 0 and 4 are both even numbers, so we have even powers. This function would then be even. So it's even because it has even numbered powers. And this would, kind of help you avoid even plugging in a negative x to begin with. Then our last one here, we have both. We have 2x to the power of 1, and then we have x to the power of 2. So we have an even and an odd number. So it's neither because it has a mix of even and odd numbered powers. So that's when it's neither, when it has even and odd numbered powers. You can't determine if it's even or odd if it has a mix. So it would just be neither in that case. But so that's another little trick that you could use as a quick way to figure out if a function is going to be even or odd, is just by looking at the powers. If they're odd numbers, it's odd. If they're all even numbers, it's even. And if it's a mix, it's just neither. So, all right, let's go ahead and head back on over to our lecture since we just wrapped up problem 4. All right, so just finished example 4, and that wraps up section 2.6. So in summary, in section 2.6, we covered shifting functions vertically and horizontally, reflecting functions over each axis, stretching and shrinking functions vertically and horizontally, and we learned about even and odd functions. So, all right, that wraps up section 2.6, and I'll see you in the next one.